Okay, so this is from 2016, number 2. And this problem here is talking about collisions. And if a student gets to this problem, if you took this in 2016 and you got to this problem and you did not know what this word elastic meant, you're going to be really stuck for the majority, if not all, of this problem. So what I want to do before we tackle this is just kind of do a background of collisions and what it means for a collision to be elastic. So let's do that. So when we did collisions, there's 2 types of collisions basically. There's elastic collisions, and then there's what we call inelastic, if I can spell. So there's elastic collisions and there's inelastic collisions. Now, all collisions, momentum will be conserved. So the symbol for momentum is P. I'll just write the word out. Momentum, which is lowercase p, is conserved. And that's true for both. In collisions, as long as there's no outside forces, you know, the only force that could be present is the force of the collision itself. But if that's true, momentum will be conserved. So we have momentum conserved in both elastic and inelastic. Now, what's the difference between elastic and inelastic? Well, in an elastic collision, mechanical energy is also conserved. And in inelastic, we would say mechanical energy is not conserved. Okay, now, just as a review, what do we mean by mechanical energy? Well, mechanical energy, there's 3 basic types that we looked at. We have potential of gravity, which is mgh. There's good old-fashioned kinetic, which is 1/2 mv squared. And then we looked at potential of spring. If you compress or stretch a spring, you can store energy, and that's 1/2 kx squared. So in an elastic collision, we say mechanical energy is conserved. The classic example of an elastic collision would be a gas molecule striking the side of a container. So say this represents a gas molecule right here. So here's a little gas molecule. The gas molecule, and this is just like, you know, a wall, side of the container. Here comes the gas molecule, boom, strikes the wall, bounces off the wall like that. If this is elastic, if this collision is elastic, basically what we're saying is the mechanical energy before the collision equals mechanical energy afterwards, which generally speaking is going to be kinetic, right? The moment before a collision, you're going to have kinetic energy. And then the moment after the collision, you're going to have kinetic energy. So if the kinetic right before the collision equals the kinetic right after the collision, that's elastic, you know? And in everyday life, we don't really see elastic collisions because that would be like, you know, you're walking down the street and 2 cars hit and, you know, they bounce off each other like, you know, gas molecules bouncing off the side of a container. It would be very, very, very weird to see an elastic collision like that in everyday life. Now, inelastic, so just bear with me. This is going to be helpful to the problem when we get to it. So let's just look at inelastic. Now, here's a situation. So say we have a block, let's call this guy M1, and let's say that M1 is 2 kilograms. And then over here, we have a second bigger block. We'll call this guy M2, and we'll say that block is 4 kilograms, and say block 1 has a velocity. So say this velocity here is 10 meter per second. Now, oh, and we'll say that M2 is sitting here at rest. It's not moving. And of course, we'll say no friction, right? Because in order for momentum to be conserved in a collision, there can be no outside forces such as friction, because that would make conservation of momentum not valid. So here we have a situation before collision. And then let's say these guys stick together. Okay, so M1 collides with M2. Let's just say that they stick together, and then after the collision, they're going to move off together, right? So they stuck together. Here's the 2 kilogram. Here is the 4 kilogram, M1 and M2, and they're going to move off with some final velocity. Now, do we have kinetic before this collision? So if we look at this situation before collision, do we have kinetic energy? Yes, we do. M1 has it. How much kinetic energy is there before collision? Well, you can do the equation. 1/2 mv squared. M is 2, velocity is 10. So what's that going to be? 1/2 2 times 10 squared is going to be 100. So before the collision, there's 100 joules of kinetic energy. Now, will there be kinetic energy after the collision? Yes, there will be, because we have a final velocity. Now, before we can calculate this final kinetic, before we can calculate it, we need to know what this final velocity is. So to calculate that final velocity, we're going to use conservation of momentum. So before collision, what was the only object with momentum? It was the 2 kilogram block. So we're going to say M1 V1 initial. That's the momentum of block 1 before collision is going to equal the total momentum after collision. So now we can solve for V final. This is going to be M1 V1 initial divided by the sum of the masses. So this will be 2 kilograms times 10, right? That's the velocity before collision. Masses combined, 2 plus 4 is 6. So this gives us a final velocity of 3.3 meter per second. So now we can calculate this final kinetic. Final kinetic after collision, 1/2 combine the masses, 6. Velocity after collision, we just calculated that, and we get a final kinetic of what? About 33 joules. So was this collision elastic? Well, how much mechanical energy did we have before collision? We had 100. How much mechanical energy after collision? 33. So we lost almost 70% of the initial mechanical energy. So this would definitely not be elastic. Okay, so let's go back to the problem, and I think that discussion will help this make more sense. All right, so here is the problem. So we got this new toy ball being advertised, and it's advertised as bouncing in a perfectly elastic way, meaning that all mechanical energy is kept, no mechanical energy is lost. A student suspects, however, that no collision can be perfectly elastic, and the hypothesis is this. The hypothesis is that the collisions will be very close to elastic for low speeds, but they'll deviate more and more from elastic at higher speeds as the speed increases. So A, design an experiment to test the hypothesis about collisions of the ball with a hard surface. The student has equipment that would usually be found in a school physics laboratory. Okay, what quantities would be measured? Now, I think the easiest way to do this, here's the setup that I would do. So here's the hard surface they're talking about, and then here is the toy ball. So if the toy ball starts up here from some initial height, if the toy ball starts up there at some initial height and is released from rest, this ball is going to drop, drop, drop. It's going to strike the hard surface, and then the ball is going to rebound to a final height up here. Now, if the ball rebounds to the same height that it started with, well, that would be an elastic collision. And here is why. The ball, so the ball here starts with potential of gravity. Because it starts at rest, there's no kinetic at the beginning. This potential of gravity gets converted to kinetic energy 100%, assuming that there's no air resistance. This potential of gravity gets converted to kinetic right before collision. Then the collision happens, then the ball leaves the surface with kinetic again, and then that kinetic gets converted back to potential of gravity. Now, of course, potential of gravity is mgh. So if these h values are the same, if those h values, the starting drop height and then the rebound height, if those heights are the same, that means the potential of gravity initial and the potential of gravity final, they must be equal. And if those are equal, that means that the kinetic before collision and immediately after collision also must be equal. So for this purpose here, you don't need to explain as in detail as what I just did, but I just want to make sure that you do understand what we're talking about. So what I just said again is, if these heights are the same, drop height and the rebound height, that tells us that the starting potential of gravity equals the ending of potential of gravity. And if those are equal, then the kinetic before collision and after collision are equal, which would be the characteristic of a elastic collision. So what we would measure is this. So to answer A, part one, we are going to measure, we will measure A, drop height, and you could even put this diagram here, call the drop height H naught, and we will measure the rebound height H final. That's what we're going to measure. Number two, Roman number two, what equipment would be used for these measurements and how would that equipment be used? Okay, for two, I would just say we're going to use a meter stick. And then what else, another thing that would be really cool, and everybody has one as long as you have a phone, is you could say a video camera, right? If you had a video camera, you could video this to get a really accurate measurement of how high the ball rebounds after the collision. All right, and then number three, we're going to describe a procedure. So here is the procedure that I wrote. So I'm gonna say it out loud, and you can copy it if you want. So mine is a three-part procedure. So A, I wrote, you're gonna drop ball from 8 different heights, ranging from small to large. Use meter stick to record the drop height. So I'll say that again. The first step of my procedure is drop ball from 8 different heights, ranging from small to large. Use the meter stick to record the drop height. Second step, using video camera. So say using video camera, record the bounce or rebound height of the ball for each trial. So record H final, HF, using video camera. Okay, then third step. Now, for these sort of questions, you always want to talk about multiple trials because that minimizes error. So my third step is drop the ball 3 times from each drop height to minimize error. So for each of the 8 that I specified, you're going to drop the ball 3 times from each drop height, just to minimize error. You really want to talk about multiple trials. Okay, on to part B. So part B says, how would you represent the data in a graph or a table? Okay, I think graphical would be the way to go. So for the way we did it here, so let's see, we have independent and dependent. So y-axis is always the dependent variable, and then x-axis should be independent. I don't know if they would mark you off if you did this wrong, but we're going to be graphing the drop height from the rebound height. So which one depends upon which? I would say that this is the dependent, and then the drop height is the independent, right? The drop height doesn't really depend on anything, but other than how high you drop it from. But the rebound height really depends upon the drop height. So we're going to go, so the dependent is going to be H final. This would be H naught. Now, describe how you would represent the data in a graph or table. Explain how that representation would be used to determine whether the data are consistent with the student hypothesis. Now, let's just review. The student's hypothesis was at lower speeds, when the ball collides with the surface, at lower speeds, the collision will be elastic, but at higher speeds, it will not be elastic. So an elastic collision would be, we drop it from this height and it returns to the same height. That would be elastic. All the energy is kept. So if that's the case, like if we drop it from like 0.1 meters and it goes to 0.1 meters, there's our data point. Like, whoa, that was elastic, right? It kept all its energy. And then we go to like 0.2 meters and it rebounds to 0.2. That's gonna be elastic. So like we're starting out with this slope of 1, right? Slope of 1, meaning the rebound height is equal to the drop height, which would be characteristic of elastic. The ball keeps all its energy. Now, the student's hypothesis is as the speed increases, the speed of collision increases, the collision becomes less elastic. So that would be like we start getting to higher values and the graph starts to do this. The slope becomes less than 1, right? So just so you understand this, like, you know, so now we're at a drop height of 0.3. We go up, but instead of the rebound height being 0.3, it's now, it's only 0.25. And then drop height of 0.4, and then our rebound height is only 0.3. Like it's no longer as elastic as it was. So this would be the what the data would show in graphical form if the student's hypothesis was correct. Okay, question C. So the student carries out the experiment as described. The student immediately concludes that something went wrong in the experiment because the graph shows behavior that is elastic for low speeds, but appears to violate a basic physics principle for high-speed collisions. So in other words, as the drop height gets bigger and bigger and bigger, let me clean this up. So what this is saying is, you know, we drop the ball from a low height right here. So here's the ball from a low height, and it's like, whoa, from a low height, it's very elastic, right? Meaning, you know, it returns to the same height, mechanical energy is conserved. But then as we drop it from a higher height, so let's move this up. So now we drop the ball from a higher drop height, and it's like this, like, okay, now the ball's like, here, it comes down, and then it rebounds, the ball hits the ground, and it rebounds up, but then it violates a law of physics, which would not be returning to like here. This would not violate any laws of physics. That would just be like, oh, we lost mechanical energy in the collision. That's inelastic. What would violate a law of physics would be a regular ball, you know, no energy stored in it, bounces and then ends up here, where the rebound height is higher than the drop height. And the reason why that violates a law of physics is because we are ending with more mechanical energy than we started with, right? So the ball here starts with potential of gravity, it ends with potential of gravity. This potential of gravity final is bigger than the initial, and there's no explanation for that that I've read. Now, what could make that possible? Well, if this ball had like a little firecracker in it, or some form of chemical stored energy, the ball hits the ground, and or maybe there's a spring in there that was loaded, and the spring releases, causing there to be more mechanical energy. But none of that was mentioned. This is just a regular toy ball. So let's answer the question. Give an example of a graph or a table that indicates nearly elastic behavior for low speeds, but appears, okay, so let's do the same thing. So we're gonna go final height, initial height. So it's elastic for slower speeds, right? Drop it from a height, ooh, it goes to the same height. Drop it from a height, oh, same height. That'd be very elastic. Now, what would violate the laws of physics would be we go to this height, and then all of a sudden we start getting like a dramatically bigger, like the graph starts going like that. We drop it from like 0.1, 0.2, 0.3, right? So that led to 0.1, that led to 0.2, right? 0.1, 0.2, then all of a sudden we drop it from 0.3, and it's like, whoa, now it's like going to like 0.5, like what the heck? Where did that other energy come from? This would violate a law of physics. Okay, state one physics principle that appears to be violated in the graph. Easy. Mechanical energy. Conservation of mechanical energy is being violated here. Briefly explain what aspect of the graph indicates that the physics principle is violated. So what you would say is that for lower speeds, the slope starts out at 1, meaning drop height and rebound height are equal. But for higher speeds, for higher drop heights, we are getting more mechanical energy final than we started with initial. That's what you would say for this question here.